Welcome, explorers of motion. I'm your guide for this journey into the forces that make our world move, from falling apples to soaring rockets. Sir Isaac Newton gave us a powerful way to understand it all. Get ready to explore Newton's 3 laws of motion and how they apply to everything from your morning commute to the orbit of the moon. We'll also learn how science uses observations, hypotheses, laws, and theories to explain the natural world. Pack your curiosity and perhaps your Jedi robe, because there is much to learn about Newton's laws, young Padawan, and the forces of motion.
Powerful they are, and everywhere they act.
Science is a systematic approach to understanding the world through observation, experimentation, and reasoning. We begin by asking questions about what we observe. These questions lead us to form hypotheses, which are testable statements that predict outcomes. Through repeated testing and refinement, hypotheses can contribute to the development of scientific laws and theories. A scientific law describes a consistent natural phenomena, like gravity, while a scientific theory explains why that phenomena occurs. Newton's laws are examples of scientific laws. They describe how motion behaves under forces consistently and predictably. In science, a hypothesis is an educated guess. For example, you might hypothesize that heavier objects fall faster than lighter ones. But when you test that idea by dropping a rock and a feather in a vacuum, you learn something different. In fact, they fall at the same rate. Hypotheses help guide investigations, but they must always be testable. They are not guesses in the dark. They are grounded in prior knowledge and observation. Scientific laws are concise statements that describe predictable relationships in nature. For instance, Newton's laws describe how motion changes when forces are applied. They're universally observed and consistently tested over time. Another example is the law of conservation of mass. It tells us that matter can't be created or destroyed in a chemical reaction. Laws tell us what happens, but not necessarily why. Scientific theories explain the why. The theory of gravity helps us understand why apples fall and why the Earth orbits the sun. These theories are supported by a large body of evidence and often contain multiple laws and principles within them. Newton's laws are part of a broader theoretical framework of classical mechanics. Theories can evolve with new evidence, but they remain essential to scientific progress. Newton's first law, also called the law of inertia, states, "An object at rest stays at rest. An object in motion stays in motion at constant velocity, unless acted upon by a net external force." This means things don't change their state of motion unless something causes them to. A ball rolling on a smooth surface keeps rolling until friction or another force stops it. This law introduces the critical idea of inertia, the tendency of an object to resist changes in its motion. Let's see inertia in action. Did you ever have to slam on the brakes and feel your body lurch forward? That's your body wanting to keep moving, even though the car stopped. Inertia depends on mass. The more mass, the more inertia. That's why it's harder to push a loaded shopping cart than an empty one. The force of friction or a seatbelt is what finally stops you. Newton's second law says the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The famous equation F equals ma comes from this law. If you apply a greater force, an object accelerates more. But if the object has more mass, it accelerates less for the same force. This law is key to understanding how motion changes in response to forces. When you push an empty shopping cart, it zooms forward. But when you push a loaded cart, it barely moves. You need more force to accelerate the heavier cart. That's Newton's second law in action. Force, mass, and acceleration are all connected. The relationship helps us design vehicles, build roller coasters, and even launch rockets. Newton's third law is, for every action, there is an equal and opposite reaction. This law explains why a rocket launches upward when it pushes gases downward. The forces come in pairs, action and reaction pairs. They act on different objects, but are equal in strength and opposite in direction. It's not just a physics idea, it's a principle you experience every day. You push on the ground when you walk, and the ground pushes back. That push from the ground moves you forward. Swimmers push off the wall, and the wall sends them gliding. Birds push air down with their wings, and the air lifts them up. These are everyday examples of action-reaction pairs. If all the forces on an object are balanced, the object stays at rest or keeps moving at constant velocity. That means there is no net force. But if the forces are unbalanced, the object accelerates in the direction of the net force. This is how motion begins or changes. In a tug-of-war, if both teams pull equally, the rope doesn't move. But if one team pulls harder, the net force causes the rope and the people holding the rope to move. Gravity is the force that pulls objects toward each other. On Earth, it pulls everything towards the center of the planet. Galileo and Newton showed that in a vacuum, all objects fall at the same rate regardless of mass. A bowling ball and a feather fall side by side in the absence of air resistance. The acceleration due to gravity is approximately 9.8 meters per second squared on the surface of Earth. So what did we learn? Newton's first law tells us that objects resist changes in motion. His second law shows how force, mass, and acceleration are connected. And his third law explains that forces come in pairs. Along the way, we've used hypotheses, learned what makes something a law or a theory, and seen how science tests ideas. These laws of motion apply to everything around us, and they help us answer questions, make predictions, and understand our universe. Keep asking questions, keep exploring. That's how science moves.